Hello students, welcome to this class of fluid mechanics. So in this class we will study about continuity equation in 3 dimensions, right? If you have not gone through my last lecture that was on continuity equation and conservation of mass, please go through that lecture first. Only then please attend this lecture. Otherwise you will not be able to understand what we are doing in this class. Okay? So yeah, in this class we will derive the relation for continuity equation in 3 dimensions. So to do that, first of all, I will consider this fluid element, right? What is this? What I mean by fluid element? Let's say this is my fluid, right? That is flowing in a pipeline. So here in this fluid, I have taken this small element on which I am going to do my study, right? So this is basically a projection of this by this cube. Fine. I hope you understand what is this thing. This is a small fluid element on which we are going to do our study, right? So let's proceed further. Right? Yeah. So let's say first mark our axis. This is x-axis, this is y-axis, and this is z-axis. Fine. Let's say this elemental length of my element, this is dx. Similarly, this one will be dz, and this length will be dy, right? This will be dy. And what's the velocity of my fluid? Let's say in x direction it's u, in y direction it's v, and in z direction it's w. Fine. Let's mark our fluid element A, B, C, D, E, F, G, H. Right. So this is a complete fluid element. I have a cubic fluid element A, B, C, D, E, F, G, H, on which I have marked my axis, x-axis, y-axis, and z-axis, and I have also mentioned my elemental lengths, that is dx, dy, and dz, and the velocity of fluid in all the 3 directions, right? Along all my axis directions. Along x-axis it's u, along y-axis it's v, and along z-axis it's w. Fine. Clear? So for our study purpose, first of all, let's consider these two faces, right? So first of all, let me tell you, we are going to calculate the flow rate for 3 different directions, right? Like that is for x direction, for y direction, and for z direction. For all the 3 directions, I am going to calculate my continuity equation separately, and then I will combine them to calculate the continuity equation in 3 dimensions. So first of all, let's talk about x direction, right? Like in this direction, in x direction. First of all, we will study about x direction. So to study about the flow in x direction, I will have to consider these 2 elements. Let me show you these 2 surfaces, right? This surface and this surface. Fine. So what's happening over here? What's happening over here? Basically, the fluid is entering in from this face. What is this face? A, B, C, D, right? Fluid is entering that the fluid that is flowing in x direction, that is entering from the face A, B, C, D, and that's getting out from our element from the face E, F, G, H, right? Fluid out It's getting out from our element from the face E, F, G, H. Fine. Yeah. So now, first of all, let's write the equation for mass of fluid that is entering through the phase ABCD. Mass of fluid entering from ABCD. What it will be? Rho, density of fluid, multiply by, we have already calculated in last class, right? What's the formula? Rho into V, velocity. What's the velocity in x direction? U. Velocity next direction U. And what's the area of surface ABCD? It's dy into dz, right? Into dy into dz. We know, right? From these two, this is dz, this is dy. So what's the area of the surface? Dy into dz. Fine. So mass of fluid entering from ABCD will be equal to rho into velocity in x direction, that's u into dy into dz. Fine. Now we will write mass of fluid leaving from which phase leaving? From EFGH. From EFGH, right? What it will be? It will be rho mu dy into dz plus d by dx of this same element, that is rho u dy dz, right? Rho u dy dz. What it means? What will be the mass that will leave the system? The mass that entered the system plus the rate of change of that mass that is happening inside the system or inside my fluid element that I have considered. The small fluid element that I have considered, the change in that mass in x direction plus the mass that has entered will be the mass that will leave the system. Fine. So what will be the gain of mass? Gain of mass in x direction. What will be the gain of mass in x direction? It will be equal to mass through ABCD, the mass that has entered minus mass that has left, that is mass from EFGH. Simple. Which means it will be equal to rho u dy dz minus of rho u dy dz minus of del by del x rho u dy dz. Fine. This will cancel out. So what will be my gain of mass in x direction? It will be equal to minus of del by del x rho u dy dz. Fine. That's my gain of mass in x direction. Similarly, what will be the gain of mass in y direction? What will be the gain of mass in y direction? It will be equal to, by similarity, right? You can calculate also, but yeah, it will came out to be similar like this. So it will be del upon del y rho, here we will take v, right? Sorry guys, we have forgotten one thing, that while calculating here, right, wait a second, then I have written this thing, the rate of change. Here we have to multiply this element with this length, right? Because what we are saying, mass of fluid leaving from EFGH. But it will be equal to the mass that has entered plus the rate of change of mass. What will be the actual mass change? The rate of change of mass multiplied by this length, right? So del by del x into rho u d by dz multiplied by this elemental length along x direction. What's that length? Into dx. Fine. Into dx. So here also it will get multiplied by dx. So here it will get multiplied by dx. Fine. So yeah. So gain of mass in y direction will come out to be rho upon rho y, rho v dx, dz and dy. Fine. Similarly, gain of mass in z direction will be equal to del upon del z rho w, right? Velocity in z direction, rho w into dy dz into dx dz. Actually it's also right, but yeah, we will write it in a similar way. So what it will be? Dx dy into dz, right? What is the net gain of mass? What will be the net gain of mass? It's the gain of mass in x direction plus y direction plus z direction, right? Gain of mass in x plus y plus z direction, which will be equal to minus of del by del x rho u plus of del upon del y rho v plus of del upon del z rho w. Fine. Multiply by, I have taken from all this, you can see that this element dy dx dz, dx dy dz, right here also, right? Dx dy dz, dx dy dz, this element is common in all the equations that we have calculated for the gain of mass in x direction, y direction and z direction. My this element dx into dy into dz is present in all the elements, right? So I can take it outside, right? I can take it as a common and we'll write here multiply by dx dy dz, right? This is my net gain of mass. This is my net gain of mass. This equation here is net gain of mass. So now if this is a net gain, mass can neither be created nor be destroyed, right? So what will the mass inside my fluid element? Very simple. What will the mass inside my fluid element? Rho density multiply by volume of element, right? What's the volume of element? What's the volume of this element? Length into breadth into height, that is dx into dy into dz. So I can write that mass of fluid element. I am not talking about the fluid entering or leaving the system. I am simply talking about the mass of that element only. That will be the rho of liquid, density of liquid multiplied by volume of that element, which is equal to rho into dx into dy into dz. Fine. And what will be the rate of change of mass of fluid element? What will be the rate of change of mass of fluid element? It will be del by del t rho dot dx dot dy dot dz, right? Which can also be written as del rho by del t, and because my elemental length is not changing with time, only density can change. Fine. If density will have to change if my mass is either getting accumulated or getting or getting shifted from from inside to outside of the system, then density has to change because my volume is constant here. That is dx into dy into dz. That's the volume of element that I have taken for my study purpose. Right. So rate of change of mass of fluid element will be equal to del rho by del t into dx dot dy dot dz. Now, this rate of change of mass of fluid element must be equal to net gain of mass, right? From where extra mass will come? We know that mass is conserved, right? So the net gain of mass in a fluid element will be equal to rate of change of mass of that fluid element. Fine. So now we will equate these equations. So what I can write? Equating both equations. Equating both equations, I can write minus of del by del x rho u plus of del by rho v plus of del by del z rho w, right, into dx dot dy dot dz will be equal to del rho by del t dx dot dy dot dz. Fine. Here I have equated both the sides, right? So now this thing will cut out as it's common on both sides. So dx dy dz will cut out from both the sides. What will be the final equation? From here we will get the continuity equation in 3 dimensions. What's that equation? Del rho by del t plus of del of rho u by del x plus of del of rho v by del y plus of del of rho z by rho w upon del z. Fine. Equal to 0. What is this? This is my desired equation. Fine. So this is my equation. This is my equation in 3 dimensions. My master equation. We will study all these generalized cases also. This is my continuity equation in 3 dimensions. Right? Continuity equations in 3D. Now this is valid for all the cases, whether the flow is steady or unsteady. It's valid in both the cases. Even if it is uniform or non-uniform, it's valid. Uniform or non-uniform, this is valid in that case also. Or if whether flow is compressible or incompressible. Fine. It's valid in all the cases. So now let's see if I have a steady flow, how my equation will change. Let's see. For steady flow, what will happen in steady flow? This element will turn out to be 0 when for steady flow this will be 0, right? In steady flow my parameters does not change with time. So del rho by del t will be 0 for steady flow. Then what will be the equation? What will be the equation for steady flow? My equation will come out to be del rho u by del x plus del rho v by del y plus del rho w by del z equal to 0. This is my equation for steady flow. Continuity equation in 3 dimensions for steady flow will be this one, right? Similarly, now let's write the equation for steady and incompressible flow. Steady and incompressible flow, right? Now we will write the equation for steady and incompressible flow. What will happen over here? Now if my flow is incompressible, that means my density is constant, right? If my flow is incompressible, it means my density is constant, so I can take the density outside of my equation. So how I can write it? I can write the equation as rho del u by del x plus rho del v by del y plus rho del w by del z equal to 0, right? So rho I can take to another side, or I will cancel the rho here. I will cancel out the rho from all the three parameters. So my final equation for steady incompressible flow in 3 dimensions will be del u by del x plus del v by del y plus del w by del z equal to 0. This is my continuity equation for steady incompressible flow. Fine. This is my continuity equation for steady incompressible flow. This is my continuity equation for steady flow. Whether it is incompressible or compressible, it's valid for both the cases. And this is my master equation for continuity equation in 3D. This is my master equation. Fine. You can apply this if you can remember this equation. You can apply it in 2D flow also or 1D flow also. Fine. There is nothing in 1D flow. Sorry. So you can apply this in 2D flow or in 3D flow. It's applicable to both. So I will advise you to remember this equation: del rho by del t plus del rho u by del x plus del rho v by del y plus del rho w upon del z is equal to 0. That's the continuity equation in 3 dimensions. I hope you understand how to derive the relation for continuity equation in 3 dimensions, and you get how we have taken the fluid element here, right? So this was these elements I have considered for the calculation of flow in x direction, right? Similarly, if let's say you have to calculate in y direction, then you will consider this element, right? This, sorry, in z direction. For z direction you will take these elements, right? This one and this one, this top element. That will give you result for z direction. Similarly, front and back side will give you result for flow in y direction. In all the 3 directions we have calculated the net gain of mass. Then we combined all the net gain of masses in all the 3 directions to get the net gain of mass of whole fluid element. Then we equated it to the net rate of change of increase of mass of fluid element. From that we get our continuity equation. I hope you understand how to calculate the continuity equation in 3 dimensions. We will make a use of it widely in further numericals and all that. Fine. So if you have any suggestions, any comments or any doubts, please put it in comment section. Thank you. Bye bye.